Dear students, let us continue our video lectures on Advanced Digital Signal Processing course. Let me share the screen. In this video lecture, we will discuss on time frequency analysis techniques that are slightly variants of Fourier transform or more elegant than the discrete Fourier transform so far we have discussed. We will see the need of defining any other time frequency analysis kind of approaches first, and then subsequently discuss them. See, if we consider a signal x of t that is like this, okay? So you can see that this x of t has different frequencies at different time durations. Assume that it has frequency, okay, omega naught, omega 1 for, no, during say the first one is duration, okay, and then omega 2 during another duration of time, and omega 3, okay, during the rest of the duration, other duration, and omega 4, okay, during rest of the duration. So it essentially encompasses 4 dominant and different frequencies, but yet 4 different durations, okay. However, now if I take the Fourier transform of this x of t, that is, okay, either discrete Fourier transform. I have sketched this in continuous domain, but this can be continuous or discrete signal of this nature. Okay, so if we take continuous time Fourier transform for ease of understanding, okay, what we get is the Fourier transform shows up, okay, very clearly the dominant frequencies of this above signal. Okay, so if this is 0, so somewhere you will get a peak for omega 1, omega say, which is the lowest frequency, omega 4, and then the subsequent frequency, okay, omega 2, and then the next frequency, probably omega 3, okay, omega 3, and then the last frequency, omega 4. Okay, so you may have 4 peaks corresponding to these locations. The amplitudes also will vary depending upon the amplitude of the like magnitude of the frequency quotients. Okay, W2 may have higher amplitude and so on. They may vary depending upon. Okay, so same thing will happen in negative side. Okay, so I am not sketching here, minus W4, okay, minus W2, minus W3, and minus W1. Okay, 1. Fine, so same magnitudes will be there here. But the question here is, say if we ask a question, during which time duration do I have omega 1 frequency in the signal? Okay, during which time duration do I have this frequency? During which time duration do I have this frequency? If that question is asked, do we have an answer from the Fourier transform? Okay, the question here is the 0 frequency, maybe say assume that if it is not this much high, okay, some DC component. Okay, so the magnitude of frequencies in the overall signal you can tell through continuous time Fourier transform. Whereas if the question is asked to find out, okay, omega 2 frequency, okay, at what duration? Okay, in the signal, then the Fourier transform has no answer. Okay, fine. Or the same is the question. So even for the questions, any frequency, okay, omega naught, okay, frequency, how much is the magnitude of omega naught frequency in the overall signal will be given by Fourier transform, but it will not give, okay, at what time. Duration. Okay, this question is not answered by Fourier transform. This is the limitation of Fourier transform, we would say. Is this limitation of continuous time Fourier transform or discrete time Fourier transform or DFS and so on? This is the limitation of any of the Fourier transforms. Okay, so now the question here is, how do we get out of this limitation? Okay, so that is one question that need to be addressed in this video lecture. The second question is, see, all the time the frequencies may not be distinct as well like this. Okay, in some of the signals, frequencies may be mixed up. So, in fact, the situation may be even more worse. Okay, so if you have a signal, something like this. Okay, so what is this indicating? This signal has several frequencies, mix of several frequencies. Okay, so at any time instance, if you want to find out what are all the frequencies, this may have omega naught, omega 1, omega 2 and so on. Okay, and the frequencies omega naught, omega 1, omega 2 may be there at any time instance as well. Okay, they are not necessarily be at only T naught to T1 or T1 to T2 and so on. This is again another X of T. Okay, with, okay, may have frequencies, dominant frequencies, omega 1, omega 2, okay, omega 3 or omega 4, okay, anyhow, at several time duration. Okay, and often, okay, mix of these frequencies is also possible. Can be there, same duration. Okay, that means if I take a particular duration, okay, if I take from duration here to here, okay, it may be mix of several frequencies. Okay, so in that way, if for a given duration tau, okay, or any time duration, can I analyze what are all the frequencies present in the signal? Will that be given by Fourier transform? The answer is no, because the Fourier transform expression, if we see, how do we define Fourier transform? If we define the continuous time Fourier transform, x of t e power minus j omega t dt. Okay, this complex exponential based continuous time Fourier transform. Okay, so what we are doing, we are finding the inner product between x of t and e power j omega t. Okay, so inner product with a complex number is a star. Okay, so especially when we have signals, the expansion of inner product is x of t into conjugate of e power j omega t dt. Okay, that's what we can write crisply this expression as inner product. Okay, inner product is same as projecting x of t on e power j omega t, complex exponential signals, as we have discussed in earlier classes. It essentially also gives the correlation with respect to corresponding frequency e power j omega t for a particular omega. Okay, x of t and e power j omega t. Okay, right. But this inner product we are not finding for a particular duration, and we are finding for all durations, across all durations. Okay. Okay, that is why we are not able to find out the frequencies. Okay, these are given at a particular duration. These are the overall frequencies. Frequency coefficients or content or magnitude in overall signal. Fine. So now if we wish to find out the frequency present in a particular duration, what should we do? We should find the inner product. If you want to find out the frequencies present in a particular duration, then x of t has to be found inner product with a window, okay, at given time t, no, and multiplied by e power j omega t. Fine, this gives us a frequency analysis over a given duration. What is the duration? That is defined by, who defines the duration? Duration is being defined by this window wt minus tau. Okay, if I define wt minus tau to be 1 for mod t minus tau, okay, less than or equal to some tau naught by 2. Okay, so if that is the case, that means if I am at this location of t, I want to analyze the frequencies at this location. What I'm looking at is, so here, okay, minus tau naught by t. Okay, this duration you can consider tau naught by t. Okay, and then this duration is also tau naught by t. Okay, so I am considering the duration minus tau naught by t to t plus tau naught by t around t. Okay, so that I am analyzing the signal information only in the small duration to understand the frequency content of the signal in that duration alone. This is referred to as short time Fourier transform. Okay, and hence this short time Fourier transform is not just the function of frequency, but is also a function of tau, because at given tau I am analyzing the signal. Okay, I am analyzing at a given tau. Since this we denoted as t, let us denote this as tau. Okay, at a given tau I am analyzing the signal. Okay, and hence this short time Fourier transform use the frequency content, okay, in that tau, in that window around tau. Okay, window is how we define window. Here we have defined it as a just a rectangular window that is exists to capture the signal only in the duration, okay, t minus tau by 2 to t plus tau by 2. Okay, right. So now another see, especially this kind of analysis is very much important for the signals which are non-stationary. Okay, that means the frequency content or the like statistical parameters of the signal vary from duration to duration. Such signals are referred to as non-stationary signals. Say, for example, the mean and variance, if I see, okay, that may be quite different here compared to here. Mean amplitude and the variance of amplitude. Similarly, the frequency content also quite varying over time with at different durations. Such signals are referred to as non-stationary signals. For analysis of such non-stationary signals, people often use this kind of window-based Fourier transform, referred to as windowed Fourier transform or short-time Fourier transform. Or windowed Fourier transform. Okay, so let me expand this windowed Fourier transform in the next slide to see more clearly what we are doing. X, okay, short time Fourier transform of j omega comma tau is equal to integral x of t e power, sorry, let us bring in the window w of t minus tau, okay, e power minus j omega t dt. T, this is from minus infinity to infinity. See what the integral is going from minus infinity to infinity, but nevertheless this tau determines, okay, the location around which we are finding the frequency content of the signal. Analyzing signal. Okay, analyzing the frequency content of the signal. Okay, so around tau, so at t equal to tau, essentially this is also a t equal to tau, we are analyzing the signal. Okay, and this is how is this analyzed? Through putting a window, that is window function, that is referred to as this is a rectangular window function. Okay, w of t minus tau is equal to 1 for mod t minus tau less than or equal to tau naught by 2. Okay, window width is given by tau naught here. Okay, so what essentially we are doing is we are finding Fourier transform for this signal, modified signal, rather than to finding the complete signal. Okay, this is the modified or windowed signal, we can say. Okay, for this windowed signal, we are finding the Fourier transform. Essentially, what we are doing is this, and hence, in practical sense, infinity, it goes only where this is non-zero, and hence minus tau naught by 2 to tau naught by 2. Okay, so you can modify this further, you can simplify this further by explicitly writing the limits of this. This implies, okay, x short time for a transform, okay, j omega. So in fact, you can write here tau or t itself, but we preferably write tau because around which we are finding short time Fourier transform, because there is a running variable here we have kept as t. Okay, so around tau, and how is it fine? By minus tau naught by 2, that is the windowing from minus tau naught by 2 to tau naught by 2 around tau, x of t, w t minus tau, e power minus j omega t dt. Okay, this we can write like this. Okay, fine. See, what is the advantage of the short time Fourier transform? If we want to analyze at any particular instance, okay, what are all the frequencies? We take a window around it and find Fourier transform of it. But however, in most of the practical scenarios, we need to analyze the whole signal as such. However, we need to analyze whole signal at different instances. We want to find out the frequencies in the like neighborhood of the signal. So what do? For analysis through short time Fourier transform, we break the signal into different time durations, okay, or frames, and then for each frame or each time duration, we compute short time Fourier transform. Okay, so what we do is, say we may break this for this into, say, duration 1. Okay, so t tau like tau naught 0 tau naught. Okay, let this be 2 tau naught. Okay, because this direction is tau naught. So let me put this as 3 tau naught, though they doesn't clearly show up in scale. Okay, this is 4 tau naught. Okay, and then 5 tau naught, and so on. Okay, so for 0 to tau naught I analyze in the first instance, I will get some frequencies. Similarly, tau naught to 2 tau naught I analyze again, I get the next set of frequencies. 2 tau naught to 3 tau naught we analyze again, and so on. So now if we want to represent this information compactly or pictorially, graphically, how do we represent is, okay, time frequency plots. That means, say, let this be the time information. Since we have broken this time information into frames, okay, so what we do is, so initially we have actually 0 corresponds to a frame around 0. Okay, so let the Original 0, instance of like t equal to 0 be here. Okay, yeah, it's okay. So assume that it is from here itself, and then this is the first frame and this is second frame and so on. Then integral simply changes from 0 to tau, or say 0 to tau naught. That's all. Okay, so you have one set of frequencies yet here. So if I so these are the frequencies around t equal to 0. Okay, so similarly you will have some other set of, this is the frequency axis. The magnitude of frequencies will appear in z axis, which are not shown here, which are shown as a color bar in plots, or they show in 3 dimensions as z magnitude in the z axis. Okay, in the third axis. Okay, so similarly the other, say this is next set of time duration is analyzed. Okay, next time duration is analyzed. Okay, next time duration is analyzed. For each of the time duration, you may have a set of frequencies. Okay, and their magnitudes may be different. Okay, so if this is f naught, so you can see that the so this may be some hedge. Okay, so this may be some hedge and this may be some other hedge and so on. Okay, so at a particular omega naught, if you wish to know what like what are the frequencies, then what we do is we put m omega naught here. Okay, so if we would like to compute x short time for a transform, okay, at a given frequency omega naught, around a given frequency, at a given frequency omega naught, what is strength of omega naught at time tau? Okay, then what we do is this is the inner product between x of t, w of t minus tau into e power my and comma e power j omega naught t. Okay, please note here I have put omega naught t. Please note the inner product can be considered, this can be considered as x of t and the inner product with wt minus tau into e power j omega t, or x of t into wt minus tau comma e power j omega naught t. Okay, both are same. In this we are bringing, like we are considering the exponential of shorter duration. Okay, so to do inner product, and in this we are windowing the signal and doing the inner product. Both are essentially same operation. Okay, and the interpretation wise, this is windowing the signal and that is taking a basis function of short duration. Okay, with windowed basis function, and it analyzes the frequencies of particular omega naught. So this may be, say for example, if this is the omega naught. Okay, so we have omega naught frequency. We can analyze this one omega naught frequency, and if this is tau, okay, what we are essentially analyzing is frequencies. So if this is tau, for example, we are analyzing the frequencies of this duration. Okay, and then at omega naught. So this essentially this is the region. Okay, this is the region where we are analyzing. This is the region where we are analyzing the frequency content. Okay, all the signal, this duration, what are all the frequencies present? Okay, at this frequency, what is the magnitude? Okay, of the frequency content. Fine. So this representation of time frequency information in time frequency plots is quite effective to understand at different durations what are all the frequencies present. Now, as you can see, I may bring, if I have a signal of some say 16,000 samples. So assume that I have a speech signal. Okay, of say 16,000 samples. Assume that I have broken this speech. I want to analyze this frequency content of this speech signal. This speech signal is non-stationary, and hence it may have It may have several frequencies at different durations, even mix of frequencies at a given duration. I would like to analyze this frequency content of the signal. Also would like to localize at what time instant these frequencies have occurred. Okay, particular frequencies, I want to know at what time instance or those particular frequencies have occurred. So I would like to apply this short time Fourier transform. So to apply this, assume that I have broken this into frames. So of say 500 sample duration. Okay, so how many frames do I may get now? If I break this into 500 sample duration, then I may get 32 frames I may get. Okay, if I get 32 frames, it means that, okay, I will be analyzing 32 windowed samples of the big original sample. Okay, so I will be analyzing each of them to be analyzed. By Fourier transform. Okay, so for each of the 32 durations, assume that I have taken, okay, we took 500 sample DFT. DFT to analyze each frame. Okay, to analyze each frame, assume that we have taken 500 sample DFT. And hence, the matrix of DTFT now will be, this implies matrix of, okay, time frequency plot, okay, time frequency information is how much? So we have taken x-axis the time. In fact, this gives the, in fact, instead of time, what we get here is the number of the frame, okay, or frame number. Okay, frame number. Okay, so this may be 0 here, first frame here, second frame here, third frame here, and so on. So how many frames we have? So 32 frames we have. So there are 32 columns. And how many number of rows will be there? We have 500 samples in the DFT. So this is a discrete Fourier transform. So we will have actually 0, okay, 1, 2, and so on. Okay, you may have up to 500 samples or 500 different frequency coefficients for a given frame. Okay, so the dimensions will be 500. Okay, these dimensions of this time frequency information is, okay, 500, 500 cross 32. Okay, so a matrix of 500 cross 32 frequency quotients. Time frequency quotients we should call now, because these are analyzed at different durations of the signal. Each of the frequency quotient doesn't infer, okay, what will happen at this duration. Both are independent now. Okay, this whatever are the frequency quotients I'm getting at this duration, okay, will only indicate the frequency content from this duration to this duration. Similarly, the frequency quotients here, okay, are indicative of the frequency content in duration 1. Okay, that means around T0 to 2 T0 or something like that. Okay. No, so please note the actual quotient strengths are in z-axis here, not shown. Okay, so that's why we are giving a number of matrix of 500 cross 32 dimensions to represent the time frequency information. Okay, at what different time durations or what are all the frequencies present. Okay, so this gives us, this is referred to as short time Fourier transform. This is referred to as okay, short time Fourier transform. short time Fourier transform matrix. What is the advantage of this short time Fourier transform over the conventional Fourier transform? It helps us to analyze each of the different time durations separately for analyzing the frequency content in that duration alone. Okay. So this is the usual procedure people adopt for understanding the time frequency information or frequency information of non-stationary signals like speech signals. Okay. So this example we have taken is a non-stationary signal or a speech signal, okay, which will mostly require this kind of analysis for understanding the frequency content at different durations. Fine. See, given this now matrix of time frequency quotients or short time Fourier transform quotients, what next we need? Say if you want to get back original signal, okay, that is if you want to synthesize the original signal x of t back from these frequency quotients at different durations, that is if we are given, okay, if we are given x of x short time Fourier transform, okay, of j omega comma tau, okay, but what we want is x of t, no, synthesize the original signal. What do we do? What do we do is, say, apply inverse Fourier transform, that is inner product with e power minus j omega t. But since we have applied at different windows here, we should also consider the same windows here for reconstructing back. Okay. And this inner product now has two parameters. When we expand it, it has one parameter that is on omega, that is x short time Fourier transform j omega comma tau. Okay, essentially this window t minus tau minus j omega t, because the inner product takes with complex conjugate, okay, this signal into complex conjugate of this dt, okay, and hence plus will come dt d omega, so integral over omega first and then tau, because we have taken at different taus, okay, what all, if this tau is taken at discrete intervals, okay, then what we have is we need to do summation here, okay, instead of the integral. If we have taken at all durations of tau, okay, then what we do is we do the integral. At what durations of tau means, given the signal, tau can be here, here, here. So I will put at all continuous durations around which I will put the window, and for each of the window I will take the frequency content. So the windows from here to here and here to here, see, may have large overlapping regions. Okay, but however, normal practice is to have a discrete windows, and hence also like this tau is often a discrete variable. Okay, in that case, summation you can use to get x of t back. Okay, fine. Okay. So now the question here is, see, if is this short time Fourier transform itself is good enough for the analysis of time frequency information, or are there any better ways of doing time frequency information extraction in the non-stationary signals or signals having different frequency content at different durations or at same duration? The answer is short time Fourier transform is a basic and simple approach for finding the frequency content at a given duration, but there are much elegant methods for the time frequency analysis or localizing the information of time and frequency in a given signal. What do we mean by localizing the information of time? That means if I give you a frequency omega naught, x of j omega naught, at what time does this frequency x of j omega naught has occurred? That is the ability to localize in time. Okay, the ability to localize in frequency means Localizing a frequency means if I give you a x of t, okay, so at what location, at what time, say if I give some x of t, what are the frequencies given at given x of t? Okay, that is localizing the content, frequency content in time. Okay, so if we want to localize in time, we should take a duration in t, and that we should be able to tell where this frequency has occurred. That also will help us to tell where this frequency has occurred. Okay, so if we see in short time for a transform, we are localizing in time. In this time, this frequency has occurred. But if I ask you this, say if in this 500 frequency components, assume that third frequency component is dominant. If we ask a question, where does this third frequency component has occurred? We can only tell that in this time it has happened, okay, in this duration, but within this duration we will not be able to tell. So there is an uncertainty, okay, in telling where does this frequency content has occurred. Okay, we are certain only up to this duration and not beyond it. Okay, there is an uncertainty in time. Similarly, if I give you a particular frequency omega naught, okay, so we if I give you a particular frequency omega naught, we can tell only in this duration. Similarly, if I give you a particular frequency omega naught, okay, so omega naught, if I give you overall, assume that some omega naught, so it may occur at any duration. Okay, so that localizing in frequency is also an important factor. So let us see how other kind of time frequency analysis help in this. So before we move on, let us see, is there any different versions of this window function? Instead of defining this window function as one for that is a rectangular function, are there any other ways of defining this window function? The answer is yes. In fact, there are more elegant ways of defining this window function as well. So we may define this window function as a Gaussian window. Okay, so it may be, say, t square by some constant. So for alpha, I am putting these values for some reasons. Okay, so I may define this. In fact, when I define it, omega t equal to 1, I can write. Okay. Similarly here, I can define just in function of t. Okay. And this is alpha is greater than 0. This is looking like a Gaussian function, and hence this is referred to as Gaussian window. This is also quite well known. And when we use this Gaussian window for analyzing this short time Fourier transform, information of frequency content of a signal, that is referred to as Gabor transform. What does Gabor transform does? It analyzes the frequency content of the signal at given time t through inner product of x of t with the Gabor window. So let us define to differentiate with respect to the rectangular window, differentiate it with, say, g of t. Okay, so g of t minus tau into e power j omega t. This is what we do. Fine. The advantage of Gabor window is that it is not like unlike rectangular window. This has a this peaks at tau, t equal to tau, and then dies down gradually through Gaussian, modulated by Gaussian. And hence, this gives more important to the current time where we analyze the frequency content and doesn't tapers off gradually like a Gaussian. Only the other time duration. And we can see that the time frequency analysis that can be done by this Gabor window is more effective. It can effectively localize the content of like the analysis of the signal in time as well as in frequency. That means for a given time, I can tell what are all the frequencies. For a given frequency, I can tell at what times it has occurred. Okay. So one more very nice feature of this Gabor window is that if you take the Fourier transform of this, okay, if we take the Fourier transform of this, it looks like again another Gaussian. Okay, so Fourier transform of Gaussian is also a Gaussian. Okay, and hence you can see that the kind of the localization that it gives in time also is there in the frequency domain. That means if it is localizing to a particular tau here, there will be another omega naught around which the frequency content is localized in the frequency domain. Okay, and we will see the further advantages of this Gabor transform. The Gabor this window function can alternatively define with additional term in the additional complex term. This complex term enables the sinusoidal signal being tapered off by Gaussian. So the window function also has a particular sinusoid of particular direction. Okay, this j omega naught defines sinusoid of particular frequency. Okay, and in 2 dimensions, it also gives us analyze the directional content of the image. So this is referred to as complex Gabor transform. The windowed Fourier transform with this complex Gabor window is referred to as complex Gabor transform. Okay, referred to as complex Gabor transform. Okay, fine. So in the next video lecture, we will understand how this Gabor window or the short time Fourier transform with Gabor window is better than the rectangular window. We will also see what are all still the limitations of this windowed Fourier transform overall. So all these can also be considered under the study of windowed Fourier transform. Fourier transform, okay, or short time Fourier transform. Here, whatever we have done with rectangular window, and this is with Gabor window. Okay. Yeah. Thank you.